Okay, so this is the start of a new project. I don't know how far I'm going to be able to get on my own, but I thought I would just try it today. I was looking for something to do. So on the left-hand side here, I've got a couple of papers open. Let me quickly explain what's going on here. So let's suppose that you have a 3D model defined by polygons, such as this awkward sweater. What this should do is to automatically split it up into small squares, where each square represents one stitch of like a knitting pattern. Then what you can do after splitting it into stitches of the right size is, for the sake of aesthetics, you can change the type of stitches you use to make patterns and stuff. Then this is the step here that I really have no idea like how it works or how to do it. Up till here, I think I could get something like kind of decent working, but this relaxation, I have no idea exactly how it works, so I'll have to read the paper. But this is, so you'll notice here that between this guy and that guy, you can see that, well, it's a little subtle here, but the types of stitches were changed up. So there's some increases and decreases in a particular pattern. And if you do this mesh-based relaxation, what it's trying to do is to kind of apply the rules of how each of these stitches will kind of like twist if you were to have actually knitted them. And so that's why this perfect triangle here became this kind of curvy thing, sort of. And then this part here, E and F, I am not doing any of these. I don't need to, although it is quite interesting. This step E, what it will do is it will take this 3D model here, divide it into these tiny squares, and for each one it'll replace the square with a B-spline representing the actual shape that yarn would make had you knitted it. So remember that each square represents one stitch, which you can kind of tell in this picture, not that well. And then this I'm absolutely never probably going to do in my whole life unless I had like a year, which is to actually simulate the 3D model of yarn and allow it to, you apply the rules for elasticity and something or whatever, Laplacians something, and then you get this, and it's like a really accurate yarn level simulation. I'm not doing that. But what I am interested in is going from a 3D model to a knitting pattern. Now, I guess I should give you a little bit more background, which is that all this started. So this paper I think is from like, oh hey, great, 2012. In 2008, I believe, there was a group of people. In fact, headed by this person, Jonathan Kaldor, and a couple other people. I think actually Jonathan Kaldor, Doug James, and Steve Marshner were the original authors of the 2008 paper, which all that was doing, well, I say all that was doing, but what that did was just the simulation. So given a 3D definition of the knitted yarn, it could be a really accurate simulation of what would happen, like the dynamics of stretching it or falling under gravity or whatever. And that was great. It's very cool and leads to some really neat stuff. But what had to happen was that the programmers had to find some way of defining this knitted model, like actually drawing the B-splines for each and every stitch. And from what I understand, what they would do is write these like ad hoc one-off scripts for every single knitted fabric that they needed. And they could kind of get away with certain things, but it was really difficult and hard to do. And if you made a mistake and your knitted model wasn't actually topologically correct, in other words, say one of your stitches wasn't properly done, it actually, under the simulation, it would unravel, which makes sense because that's what would happen in real life. Although it would unravel in a pretty catastrophic way. The author of this paper, the first author, I believe the name is pronounced Jem Yüksel, showed a video of the simulation going wrong if one of the stitches was off, and like the yarn just like flies out at these crazy speeds. Anyway, that's not important. So 2008, later updated in 2010, these three people create a really nice yarn level simulator, but they don't have a nice way of actually creating a yarn level model, like the 3D model in the first place. That's what this paper does. But there's one more thing still missing. That's what this second paper is. I believe between Jem Yüksel writing this paper and the first author on this is Kui Wu. Well, I don't exactly know how to pronounce that. I think between this and that, Jem actually became a professor at Cornell, and Kui Wu was a grad student. Anyway, this is from 2012, and this one is from 2014, and it's the name implies exactly what it is intended to do. It's actually really neat. And so here, it's a little bit hard to tell. Maybe I could find a better example in here. Actually, this is a really great example. So let's say that you wanted to knit a tube. Well, one way would be to spiral the stitches up the tube like this. And this is actually like knitting in the round. This is how you, as a human being, would be able to do it with a pair of knitting needles, or to be precise, with maybe like a circular knitting needles or double-pointed needles. But it's a lot easier for this paper to just do these stacked rings of stitches, and it's a little hard to tell, but you can convince yourself that if I follow this row here, I don't know if you can see my cursor very well, but if I follow this row, it will actually make a closed ring of yarn. So actually we have 1, 2, 3, 4, 5 closed rings of yarn, versus this model, which is actually one yarn that spirals through the whole shape. Now, in this paper, for simplicity, they don't care about knitting stuff by hand. They only care about making a model that is feasible for simulating with the Caldor simulation. But, like I say, in 2014, Kui Wu and Hannah Swan took this work. I believe they were supervised by Jem Yüksel. They took this work and actually do some kind of algorithm. I'll have to read the paper to understand it. To actually create like a hand knittable pattern from a 3D model. And this is my ultimate goal. So I need to basically implement both of these papers. Well, not completely. I don't need to implement it completely because it is already implemented. And I have the code for it right, hold on, the code for it right here. Now, I don't have to implement it myself. I could just get this code working. I mean, wish me luck. This actually looks like a really nicely done repo, but it depends on a bunch of libraries to work. And you know, I think just installing, well, actually these two, well, actually installing Nano GUI is probably quite difficult. Installing PSG32 is trivial. Installing this is probably extremely difficult. Installing this is impossible because I need a license. I could apply for an academic license, but I'm not doing that today. This is included in the repo, and then this is a fairly simple one to include. But yeah, because of all these external dependencies, it's very difficult for me to use this code, and I would probably spend like ages getting it working. And that would be nice, because this is a really cool piece of software that would be really useful. I wonder if I could find a picture. I think there's a picture of it in the paper. Wait for it. Here it is. This is their software. This is how, I don't know who this is, how somebody took the Utah teapot and actually knitted it. Like, it even has this step-by-step guide that you can follow one stitch at a time for how to knit it. It even has like a little reminder video of how to knit the types of stitches, like the increases, the decreases, and all that. Yeah, so that's what this software is. And it also has a lot of other stuff that you can do too. But yeah, I am trying to implement it myself. On the one hand, maybe I could get something useful working, and hopefully I could package it as a sort of more easily distributable piece of software, because although this is really well done, it's not easy for just arbitrary people to get it working on their computer. And also I just want to learn about it. So, okay, how long have I spent explaining what I'm doing? Let me take a look here. 10 minutes. That's not bad. I could have done worse. So yeah, let's. Today my goal is simply to kind of get like a workflow set up of where I'm going to compile my code, what language I'll use, what 3D editor I'll use, and you'll notice here that I have Paint 3D on the right hand side. I've never used Paint 3D before, except like once when I needed MS Paint and opened this by accident and just decided to roll with it. Yeah, so yeah. I guess maybe what I'll do is, by the way, well, I guess you may or may not have seen it, but I found a solution to my problem. If I were to go into a new tab here and like type something, you'll see all of my suggestions, which, is not great. Even if you do an incognito window, it still shows like your history, which is like kind of frustrating. But I found a solution. I have a Chrome window that you can't see on this stream, and I'm going to type my searches in here, and then move the tab over to this window. So anyway, let's just go and find like a simple 3D model. I know of one that I used from, I think it's, what is it called? Free 3D, I don't know, freegameart.org or something. Now, where is that? OpenGameArt, that's it. And I think there's like low poly animals, which are really nice. I really, oh yeah, here they are. They're so nice. These are such charming models. And they're even animated, although I have no idea how to animate 3D models. Yeah, dude, look at that. Isn't that nice? They're so nice. Yeah, so I think I'll start with, I really love this fox, and ardent followers of my maybe ill-advised YouTube channel will know that I've used this fox model for some other stuff. But anyway, I think I'll use the chicken because it's a little bit simpler. And yeah, so let's download this. Okay, let me do my other trick again here of moving a tab over. Okay, so let's create, I'll do C++ for now, and I'll call it, I don't know, stitch meshes, why not? Oops. And do that. Cannot find or open. Okay, I don't know what that was about. And here's the OBJ files, so let's find the chick, which clearly here was drawn in Blender. Oh yeah, duh. I also need this on my computer. Actually, I think I've already got it downloaded. Let me just check before I download it again. What's it called? Animals pack. Now, I don't seem to have it, so I'll just download it here. Yeah, I really love this these 3D models. They're just so, I don't know, charming. Okay, so now let's go here into my Paint 3D. Is this going to work? Well, I don't need it. let's skip that for now. I'll play with that later. Oh, look at that. That's cool. Now, how do you use Paint 3D? Okay, I can write on it, which is of limited usefulness, honestly. Okay. I can select the object. Nope. Oh, okay, if I hold the middle mouse button, it pans. The right mouse button. Oh, that's nice. Pan. Oh, Alt. How do you rotate? Mixed reality. What the hell is that? Okay, well. Oh no, this is. Oh, hey, that's cool, actually. No. What the heck? Like, what the heck is this? How do you rotate? I'm just gonna have to look this up on Google. Paint 3D rotate view. Using the pen, touch, or mouse, you touch the icon on the side of the pen. No, but this. Oh, maybe. Okay, so maybe. Well, rotating the model or rotating my view are. You know. Oh my goodness. Anyway, this is one way to rotate it, although I don't particularly like it. You need to use the mixed reality. Oh my god. What is this bullshit? Oh my god. It opened up a separate piece of software here. Hold on, let me just show it to you. I've never even seen this before, this thing. Can you see that? Ooh. Why on earth would this need my camera, this 3D viewer? Man, this is some... Oh my god. Also, I can't seem to capture the window for some reason. Oh wait, am I... Oh, it's just loading, I think. If I do this and wait, does it show up? Man, this is some really jank stuff. Oh my god. Alright, forget it. I give up on that. It's mixed reality. Get out of here. Okay. So it seems that I can only rotate it if I open it in that mixed reality thing. Man, this is just ridiculous. Well, I guess the only thing I need Paint 3D for is just for seeing the models Except it would be really nice. Do I even have Blender on this computer? Yeah, I kind of refuse to use Blender, honestly, because it's so freaking complicated. But I was kind of a little disappointed with Paint 3D. Like, I can't like edit individual vertices or faces. Like, oh, here we go. Okay, you have to click this toggle between 3D views, and then you can use the right click to rotate. Settings. Okay, now I need to look up Paint 3D. I mean, I don't need to edit the vertices, but I at least want to see them, like where they are. I don't think you can. I just think this software just doesn't have... Like, why is it that the only 3D modeling tools are like Paint 3D, which is a little bit, you know, not good, or Blender, which is too friggin' complicated for mere mortals like myself. Anyway. Well, maybe what I'll do here is kind of draw on it. Let me try and draw what it is I'm planning to do today only. Like, in other words, what my goal for today is. For now, all I want to do is just split it up into a smaller grid, even if that grid is not like ideal, right? So if I do something like this, like take every single face and split it up into a grid. And we're going to do this incrementally. I don't even know like where to start. What am I getting into? Maybe, okay, first of all, let me refresh my memory on the OBJ format. So there's all these like, I don't know. All right. Wait, no, yeah, I always forget. OBJ file format. It's pretty simple. Like, once we get into the vertices, like, you just define each of your vertices, and then you can refer to your, oh, and the vertex normals. That's kind of handy, actually. And then for each of the vertices, oh, interesting. For the faces, I think this is to select the material? Anyway, let's, whoops. Okay, list of geometric vertices. So yeah, vertex, texture coordinates. Ah, interesting. Do we have these in here? I don't think we do because, yeah, we're not using textures, we're using a material, whatever that is. Ah, texture coordinates. Ah, that's the normal. Fascinating. All right, let's see if we can just bitbang a OBJ file. We can't seem to edit it inside Paint 3D, which is kind of bad, but whatever. Okay, let me open up just a text editor. Or, well, actually, I suppose I could just do it in here, which, you know, whoops. Just like, I don't know, we'll call it test.obj. And we'll start with a vertex at 0, 0, 0. And let's just see if we can draw a square. So and I won't worry about vertex normals right now. Does that work like that? Is it 0 indexed or 1 indexed? 1 indexed. Okay. Honestly, this is so simple. Let me just paste it into a file directly here. I won't bother to change my OBS setup here. I'll just do it. All I'm doing is I'm saving this on my hard drive somewhere. And I'll just call it... I don't know. Okay, so now I can go in here. And I just saved it in this folder. Huh. 0, 0, 1, 0. Oh, whoops. Yeah. Interesting, though, that it like self-intersects. And you can't refresh the file. Oh no, I made it worse somehow. Oh, I see, it's a little typo. Okay, this is less than ideal, but it's good enough. Okay, great, we have a square. Let me just paste back in. You know what? Fine, I'll just change my OBS layout. Where is that? No. That's weird. How come this window doesn't show up in the list of windows? So first, let me just paste in here what I have so you can see it at least while I figure out how to use this friggin' thing. Oh, here it is. It just randomly, it didn't show up earlier, but now it is showing up. Don't ask me why. What the heck, why? What's going on? For some reason it's not capturing the title bar, but anyway, let me zoom in here so you can see. Now, what I need to know is in Paint 3D, if I were to make a grid, would I even be able to see it? So let's put some more vertices. Geez. So let's do this to make my life a little easier. Now, we need 1, 0, 0. Oops. And then I need 2, 1, 0. Oh man, this is getting hard to do in my head. Then I need 1, 2, then 0, 1, and then 1, 1. So now if I do, oh my god. Okay, first if I, this has ruined the file if I do that. Okay, it looks the same, it's still a square. So let me just put in the vertex numbers or else I'm going to lose my mind. And actually, since I have Paint 3D open, I may as well use it. So, hello. Dude, what is this garbage? Oh, wait. It just started showing up. It's just like, doesn't work. It's only drawing on this center line. Oh, is it because my shape is like, wait, hold on. From 0, 0 to 2, 0. So 0, 0 to 2, 0 to 2, 2. To 0, 2. I don't know. Anyway, so let's, instead of doing 1, 2, 3, 4, let's go 1, 5, 9. Oh boy, this is tough. 8. And then now let's do, well, the 5 and the 9 will be common. 5, 9, 5, 9, and then this one here I need 2, 1, 6, and here I need 2, 0, 2. Let's try that. Oh my god, it crashed. Oh my god. Garbage. It'll probably just crash again. Oh, this time it didn't crash. Don't ask me why. So yeah, you can't see that there's a vertex here. Although I can draw on this now for some reason. Oh my god. Why is this so broken? How hard would it be to install Blender anyway? Maybe there's like a simpler 3D editor out there. Simpler Blender software. Unity. Don't have that. I just want something simple. Maybe there's something on portable apps. Well, there's Blender Portable. How big is it? It's not too big because I don't have a lot of space on my hard drive. Oh my god, it's a gig. Yeah, forget it. Do I really want to try this? Oh, actually, wait a second. I have an idea. Linux JViewer. Maybe I could use something inside the replet. F3D. Okay, great. Let's see if I can use that inside Replit. Never heard of it, but seems like what I want. Ah! Whoa. Okay. Well, actually, I probably don't need this anymore. How does one use F3D? There is no menu that I can see. Wait, how come that worked a second ago, but now it doesn't work? That's strange. Let's just try doing that again. Okay. Oh, hey! Check that out. Ooh, it's not what I wanted. Alright. Now, let's go in here and just see what happens if I paste in this. I gotta look up how to actually use it. User documentation. What the heck? This is weird. Man, it almost works. Alright, one more thing I want to see here before I give up on it. I was just reading the options a second ago. Nah, it doesn't show me the vertices either. Okay, well. I mean, it seems like almost what I want, but it just doesn't work that well in Replit. Okay, that is something. Doesn't really work. All right, next. Open 3D. Well, actually, I mean, I don't want to install it on my computer because I don't have space, but, you know, like, there's no way this will work. Yeah, okay. Well, that's too bad. Man, I need a friggin'... Man, this sucks. I just need a 3D, like, viewer. It really just... Oh, actually, wait. I could use F3D in Windows. That might work, actually. Download. Windows. It's just an exe, so hope this doesn't, you know. Yeah. Just run the exe. Setup. Interesting. Actually, F3D seems pretty good. Okay, it might not work inside Replit, but maybe it'll work on my computer. So let's go back to this layout. Let's close this. And then let's go F3D. Hey, cool. Please. Man, I really hate the drag and drop idiom. Well, I don't hate it. I just, you know, don't like it as much. Okay. Oh, yeah. No, I don't want that. This. Okay. Let's just close this Paint 3D junk. No file provided. All right, let's provide one then. Well, I gotta browse to it. Okay. How do you see the individual vertices? And also, let me change this back to editing the vertices directly. So let's say I edit this. Let's say I comment this out, save it. Doesn't reload. Oh. Okay, hold on. Let me go look up the documentation on this again. F3D. Simple interactions with the displayed data is possible directly within the window. Click and drag to rotate around. Hold shift and click and drag to rotate the... Hold on. Hold shift, then click and drag horizontally with the right mouse button to rotate the HDRI. I don't know what that is. It doesn't do anything. Click and drag vertically with the right mouse. Oh, to zoom in and out. That's neat. Okay. Click and drag, I don't know, move the mouse wheel to zoom in or out. Oh yeah, okay. Click and drag the middle mouse to translate. Okay. Click with the middle mouse button to center the camera on the point under the cursor. Doesn't do anything. C, cycle between coloring with array from point data to cell data. Doesn't do anything. S, cycle the array, the array to color with. Cycle the component of the array to color with. Doesn't do anything. Oh my goodness. B, display the scalar bar. Ray tracing options. Volume rendering. That doesn't work either. Opacity function. That doesn't do anything. It keeps just saying ray tracing options can't be used if F3D has not been built with ray tracing. Oh hey, we got a frame counter all of a sudden. Oh, I get it. I press R to turn on ray tracing. Okay, I get it. Display the file name. Okay, yeah, so I pressed R to toggle ray tracing off, so now it doesn't give me that error. Oh, hey, anti-aliasing. That's cool. Display the cell edges. Hey! Finally, this is what I needed. Great. So you press E for that. Oh, H for a cheat sheet. I should have guessed that. I guess I don't need the axis. No, what I actually don't want is the grid. I don't really think I need that. Metadata. Blur background. Doesn't do anything. Trackball. Print scene description. Reset camera to initial parameters. Play animation if any, except there isn't. Oh, hey, reload. Oh, that's cool. That's cool. Great. So, yeah, now if I draw the rest of these, so 6, 2, and so this is 2, 1, 0. Oh. No, I actually want 6, 9, 2, this is 2, 1, 0, 1, 1, 0, so now I need 1, 2, which is 7, then I need 2, 2, which is 3, and then finally so I did 6, 9, 7, 3. So now I'll do 7, 9. I'm trying to go clockwise for each one, not that it matters. And then this is 0, 1, which is 8, and then 0, 2, which is 4. Now if I reload and press E, look at that. Great. This is going to work for what I need. Unfortunately, F3D doesn't work in Replit, which is a pain. We'll just have to deal with that. Now, let's... So, I've got to think about this. We have a way to look at 3D objects. Now what I want to do is take a 3D object like the chick, for example. And let me open it here. Where is that? Okay, great. Oh, cool. Really neat, actually. Actually, what's going on with my mouse? Why is my mouse locked to the diagonal? Wait, what? Wait. This is a problem with my mouse, like, not with the software. Oh my god. Wait 1 sec. Let me unplug it and plug it back in. Oh no! Okay, I just jiggled the cable for my mouse. Now it's working again, but this mouse is now not gonna work forever. Man. If I had a soldering iron, I might be able to fix it, but I don't. Maybe I could find one to use in town. Anyway, I wish there was a way... Oh, actually there is. Let me do this. Okay. So all of these vertices, they kind of lie between -2 and 2. Some of them are quads, some of them are triangles. So I want to take an arbitrary polygon and split it up into smaller squares. There's a problem we'll need to fix, which I'm not planning to fix today, which is that it would be nice if, like, so like you see here, like if I wanted to place a square here, like it would kind of span both of these shapes. You see what I mean? Like if everything was quad, well, even if everything is quads, like let's find yeah, like here for example, like here my stitches would be like sort of an awkward shape. Let me just take a quick look at the pictures in the paper and also maybe the text in the paper, which I should do at some point. And see if there's an explanation for how they deal with that. Unfortunately, it's probably the kind of thing where it's like, oh, every self-respecting computer artist or computer graphics person would already know how to split it up. It's probably, I think this is what Subdivide Surface does or something. So yeah, here, can't zoom in any more than that. If we take a look at this triangle face here, there's like this dotted line where it makes like a pentagon, which actually, here, let me show you that, what the meaning of a pentagon is. A pentagon corresponds to an increase or a decrease. So these are all increases here. Maybe there's a decrease somewhere else that I could show. Oh yeah, here's one. So yeah, so I guess what they did on like this particular, and it's too, man, I can't zoom in any more than that. And maybe I could draw it. So like, if they have a rectangular face, followed by like a triangular face. Wait, hold on, what does it look like? Well, yeah, so theirs looks a little bit more like this, right? So what they do is, oh, fascinating. They split it up into like this. Let me just draw all these in. Or well, just like that's fine. Right, something like this. Anyway, you get the idea. I'm not doing a great job here of drawing it up, but you get the idea. And then this, of course, is just divided into a grid. Now, instead of having these triangles, which are, not great, what they do is oh, there's no erase. Oh, there is an erase, yeah. What they do, oh my goodness, that's not what I wanted. Or whatever, I'll just color it in. They make these pentagons decrease stitches. Like that. So that's how they deal with triangular faces. Now, there's still a little bit of mystery involved here, because how do they decide that this dotted edge here is the one that should be combined to make the pentagons? Why not this edge or that edge? Maybe it's arbitrary, maybe it isn't. So yeah, let's see if there's any discussion about this in the actual text of the paper. I kind of glanced over the first couple sections earlier, but I didn't finish reading, so I read all this, I read this. This is where I stopped reading earlier today. The aim of the interactive modeling is to design a stitch mesh, blah, blah, blah. Given an input mesh that represents the surface of the garment model, there are often many ways it can be knitted to provide the user direct control over the knitting direction over the surface. We begin our modeling process with labeling, during which each edge of the input is labeled as either a wale edge or a coarse edge. Oh, that's interesting. Ah, okay, that explains a lot. That explains everything. Okay, I need to explain this wale edge and coarse edge. It's pretty simple. These are just terms from knitting. Coarse is this direction, wale is that direction. Do I need to explain more? I don't think so. Now within each stitch unit cell here, you'll see how some of these edges are bold. So this edge is bold, that edge is bold, this edge is bold, that is bold. These are known as wale edges because that's where the incoming, I don't know how to explain this, the incoming tail or the incoming yarn for this row goes in, we do some stuff, and then comes out. In other words, these wale edges, of which there are exactly 2 per stitch cell, these wale edges define where the row is. So what this means is when you're fitting all of these stitch cells together, you have to line up the wale edges together. Oh, and by the way, there can be only one yarn connection in each wale edge. Right, so that's how you put them together. These unbolded edges are coarse edges. They're what connect the rows, right? So there's this red row that connects to this green row, and this green row connects to this red row, right? The coarse edges are what connect the row that this stitch is on to the row above it or below it. Now, for these increases, we go from 1 coarse edge on the bottom to 2 coarse edges on top, from 1 stitch to 2. I just realized we're looking at a pretty unflattering angle of this chick here. Let me just fix that. Anyway, so yeah, that's what's going on with coarse and wale. Now here, it seems so, excuse me. This is the input model. Oh, wait. What? Hold on. I just alt-tabbed over to my YouTube like streamer thing, and it does not look the same as what I see on OBS. Or maybe it's just like super far behind or something. Oh, it is super far behind. Oh yeah, okay. Sorry, I got scared that something went wrong with the streaming window. Okay. Anyway, where was I? I got distracted there. Okay, A is the input model. B, C, and D are examples of possible rows, each of which is displayed as a disjoint piece with a different color. Yeah, so for example, this, let me zoom in as much as I can here. This red piece up here, these edges that connect the different segments of this red ring, these would be whale edges. Same thing for this orange ring, same thing for this yellow ring. And basically, it should form, I guess it doesn't have to form a closed loop, it does have to form like a ribbon, so to speak. It has to, because every polygon here has exactly 2 whale edges. So although, for example, here, it almost looks like we have this bizarre thing, like these edges here on the yellow are not actually connected by whale edges, so it kind of goes like up, connects here, back down, and then around. Now, why you would knit it like this is, well, I'm not sure why you would knit it that way. It would seem to be pretty difficult, but it is an option. So yeah, okay, that's part 1 is labeling. So actually, it wasn't arbitrary. This edge here becoming pentagons in the picture at the top is exactly because if this is a whale edge and this is a whale edge, hold on, I gotta think about it for a second. What does this mean for which one the whale edge is? I think, let me open up my drawing here. I think this has to be a coarse edge. This has to be a coarse edge. This has to be a coarse edge. So that means that the whale edges, which I'll draw arbitrarily in green, right, are like this. I said coarse out loud, but I meant was whale edges. So the whale edges are like this. That would be my guess. Although it would be possible to say that this is a whale edge, and then these 3 are coarse edges. I mean, that's perfectly legal, and I actually can't tell just from the picture which ones are the whale edges. So actually, no, I'm still back to wondering, like, why this is the one that was defined to have the increases and decreases. If I had to guess, these bands, because you can see there's dark bands and lighter bands. If I had to guess, the bands of the same color are in the same row. In other words, they're connected by whale edges. So we have a whale edge ring going all the way across like that. So actually, it looks to me like this is just a really friggin' weird decrease. And actually, like this one stitch here, you can see that there's a hole in the final, you see, right here. In fact, I wish I could zoom in more. It's very, very hard to see, but actually there is a higher res picture on this website. Oh yeah, this is one of my favorite pictures of all time. It's not higher res. think there is a gallery here somewhere. But it's not in the gallery. That's really too bad. That doesn't help. All right, well, this is as close as we're gonna get. Based on my knowledge of knitting, it looks to me like, so I'm following with my mouse here. Actually, hold on, I could do this in, hold on, I'm just gonna grab this with the snipping tool. And then I think I can just paste it in here. Hey, cool. Okay, yeah, it's blurry, but we can work with this. I think, man, it's very, very hard to tell. But I think that the stitch, oh my goodness, that's super wide. Oh my God. Man, I'm having so many like stupid technical problems here right now. Okay, now where was I? I think that this is, you see these lines here? I'm kind of struggling to draw them. Let me try and do a better job here. See this, oh no, not there. Shoot, I messed up. It's really, really hard to tell. But like, do you see these lines? Right? This is the same stitch over multiple rows. You see what I mean? And when we get to this famous buddy right here, I think all of these are increases along the way. So this is, you see what I mean? I'm drawing it really badly here. Like this stitch here, you go forward a couple rows and then you increase it, right? And now you increase it again on the next one. You see what I mean? It goes like this. And then when we get to here, I think what's going on is there is, oh, what is this? I think what's going on is, man, I really can't tell. Well, now how come the colors are different? Wait. Oh, because, right, this has the actual stitches. Yeah. But yeah, I think along this row here, well, no, how can that be? Oh man. But yeah, this definitely looks, all right, do you see that? This right here? And it's very, very, very small. I really have no idea how clearly it's coming across, but each of these guys here, it looks like there's, here, let me grab this and the snipping tool and color over it. Right? It looks like we've got one coarse edge back here, making two coarse edges over here, right? So it actually looks, I mean, that's my theory, right? That the whale direction is like this, and then when we get here on this row, we increase. So now we have 2 stitches, and 3 stitches, and 4 stitches, right? Like that. And so when we get to this bizarre region here where all the polygons meet together, we have an increase on this row. Now here, this is strange. This is a whale edge. It has to be, right? Because if this is a coarse edge, this has to be a coarse edge, right? Or I'll put it differently. If this is a whale edge and this is a whale edge, then that needs to be a whale edge. So what we have here is an no, this is so strange. Wait, we have two adjacent whale edges like that? Is that even legal? Well, it's got to be. So what the heck is this kite right here? Like, which one? I just don't get it. So we do our one final increase, which is this. This is our one final increase right here. And then what? Oh, right. I think I see what's going on here. Yeah, you see here? Mismatched whale directions. Yeah, this is what's going on. I think what's going on here is that this whale, like, wait, which one's course and which one's whale? I thought I had it right. Oh, shoot. I have had course and whale backwards this whole time I've been talking. Whoops, I'll bet that was super confusing. That's going to be hard to fix. In my mind, that is. Wait, no, hold on. No, I was right. Whale edges are shown thicker than coarse edges. Oh, okay, I've been saying it right. Like, this is the whale. Oh, I get it. The edge is parallel to the whale, but it's what connects the course. That's confusing. Anyway, what's going on here is that we basically have two whale directions feeding into each other. So if I go back in here, right, here this is going like that, but then here that's going like that. So, or they're not facing into each other, but they're facing away from each other. And when they face away from each other, you make these closed loops to, make it work. So, I mean, it's virtually impossible to see, but there's like some closed loop in here. Yeah, I don't know. I give up. I'm tired of looking at this, but anyway, it was useful to look at, and yeah. But what I'm interested in is, okay, let's keep reading here. So, labeling, during which each wedge is a whale edge or a coarse edge. We require that each face of the input mesh is assigned exactly 2 whale edges, and the rest of its edges are labeled as coarse edges. This way we can uniquely identify or uniquely define the knitting direction over the entire face such that the yarn curves enter the face from one of the whale edges and exit the face from the other whale edge. The collection of faces that are connected by whale edges are called a row. Yes, thank you. Hence, the labeling process conceptually separates the input into a number of rows as shown in figure 10. Yeah, you see, number of rows. If the input mesh cannot be separated into a number of rows according to the user's intentions, we require that the input mesh topology be modified manually as desired. Therefore, the input mesh must be modeled with the desired row structure in mind. Interesting. In our implementation, we use a number of high-level tools for the labeling process so that a typical input mesh can be easily labeled in a matter of seconds. In our system, the user begins labeling by selecting a border edge of the input mesh as shown in figure 11. Yeah, okay, so I don't really care about this. This is just an implementation detail. Actually, I want to see what happens at this intersection here of the 5 polygons. This is a great paper, by the way. Where was that? So right here. What the heck is going on here? It just comes out as an increase. Oh yeah, I see it now. Oh wow, cool. What about this little triangle right here? It also comes out as an increase. It gets merged into a pentagon with this other guy. Okay, so here they drew it as a dotted line, but here they didn't for some reason. But it's actually the same circumstance where we've got like a clipped triangle that has to be combined into a pentagon on the other one. Something really good came on the YouTube autoplay. Let's see what it is. It's well, I think everyone knows how to pronounce it, but it's Sewer SLVT with the song called New Love. It's pretty good, actually. I like it. Anyway, yeah, I'm a little baffled on this first step here when they make the mesh, how they decide to do triangles versus squares. Like, so here, this is a coarse edge, that's a whale edge, another coarse edge, and a whale edge. And I guess this is like a sort of an awkward trapezoid, so... Oh, I get it. The number of divisions along the whale edge has to be exactly the same, because for every row that passes through this face, it has to enter the row, then leave the row. So that sets up a constraint that the number of divisions here has to be the same. So if this edge is longer than that edge, then the stitches here are going to be taller than here. Fine. It's up to you as the designer of the original polygon mesh to define your shape in such a way that it's even possible to, put the stitch mesh on it. Like, it's not going to work 100% of the time and for any arbitrary input. And then I guess there's some heuristic that figures out how wide each stitch is going to be. Which means that at some point, yeah, if there is a difference between the number of coarse divisions up here and down here, in other words, the number of stitches along that row, then that's when you're going to need some increases. Or decreases. So like, let's say that the whale direction was actually up. I happen to know it isn't because I saw that picture, figure 11 there from below. But if this was up, then these would actually be decreases. Yeah. uh, hmm. So let's like this triangle here, obviously, this actually has 0 like guys up here, and 1, 2 stitches, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stitches down here, right? So from 0 to 10, every one of these rows has to have an increase. And oh, very cool. I just realized something. So to go from 0 to 10, we have to have 10 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And every row has an increase, which they do inside the polygon by making it a triangle. Yeah. Yeah. So there's an additional constraint here, which is that so along the whale edges, we have to have the exact same number of rows. And the difference in number of stitches between the last row and the first row has to be equal to the number of rows, plus or minus 1. There's an off by 1 error to be made here, but oh, that's not true actually, because if it's a really slight increase, maybe you only have to increase once every 2 rows. And what would that even look like? Ooh, no, that's not what I want, actually. Whatever. So let's say I had a really slight increase like this. So maybe I would do, so I've got 1, 2, 3, 4, 5, 6 stitches, and let's say that on the bottom I need to have, well, I'll just draw them in here and then count them. 1, 2, 3, 4, 5, 6, 7, 8. But, oh, yeah. So I need to increase by 2 stitches, but I have 1, 2, 3, 4, 5, 6 rows to play with. So let's arbitrarily put the increases here and here. I just picked those kind of at random. So these will be quads for this row, and more quads for this row. Now in this row, we need to have a triangle like that, I guess, because there's an increase in that row. Now we have quads again. And then another increase. And I guess it doesn't matter what side you put the increase on, but I just put it here arbitrarily, and there we go. Well, kind of. You know, you get what I mean. Now, if the whale direction is this way, then what will happen is on the adjacent face here, if we have a quad there, these will get merged like that. Well, actually, it doesn't matter which way the whale direction is, I just realized, because whether it's up or down, it will still merge these triangles with the quad on the next face. So that's another constraint. All right, I'm going to start writing this down. There might be a list like this right inside the paper, but stuff for each input polygon, num stitches on both whale edges must be equal. The number of increases, all right, well, I'll say it like this. Number of stitches on last row minus such as, all right, let's just do this. Stitches on last row, and put that in absolute value, minus stitches on first row must be less than or equal to stitches on whale edges. I'm going to fit that like that. Input polys. This is not an absolute requirement, but for simplicity, input polys will be tris or quads. And now the other thing too is that, where is my drawing? I don't think that we can connect, like let's say I drew a triangle on one input polygon. I don't think we can connect a triangle to a triangle. I think we have to connect a triangle to a quad no matter what. Let's think about that and see if that's true. So let's say I had two triangles like this, for example. And let's say that the, let me just draw in the whale edges. This is super random. YouTube, sometimes when YouTube makes an automatic mix when you're listening to music, it'll play a bunch of music in the same genre, and then randomly it'll drop in a song that you listen to fairly often that's just like totally unrelated to the genre you're listening to. So I was listening to like Death Brain, Seward, well, SLVT, and stuff like that. And then all of a sudden it's playing the soundtrack to Risk of Rain 2. It's like, well, like, I like it, but, you know. Anyway, to get back to it here, these are the whale edges. And let's say that we have 1, 2, 3, 4, 5, 6, 7 rows. And we need to go from X stitches to 0. Well, the most stitches we can have is 7. So 1, 2, 3, 4, 5, 6, 7. I kind of did this badly here, but 1, 2, 3, 4, 5, 6, 7. Wait, what? Anyway, I think you get the idea. I mean, I just drew it really badly. Let me just try and fix it up, but I think you know what I mean. So we'd have something like this. Okay. And then let's say, I mean, I'm just saying this for the sake of example. Let's say that we put our triangles like this. Wait a sec. Oh, oops. I see what I did. We put our triangles. Now hold on, I need to have 2 stitches here. Or maybe not, you know, maybe, well no, let's say I want to have 2 stitches here, so I do this, like that. Then let's say I want to have 3 stitches here, and then 4 stitches. Oh, now I'm starting to see it. Well, you know, you'll have to forgive the bad drawing here, but... So can we merge adjacent triangles? Of course. In fact, I would consider that desirable. I mean, now we just have super simple, like super simple stitches. If we merge these triangles, it all becomes nice quads, no increases or decreases or anything. So no, actually there is no constraint that we need to always pair these triangles with adjacent triangles. We can pair them with quads or other way around. We don't have to pair them with quads, we can pair them with triangles. If we pair them with triangles, we end up with normal stitches. If we pair them with quads, we end up with increases or decreases depending on what direction, what the whale direction is. Okay. So, how do we do this? Well, let's go back and read the paper, I guess. The collection of faces that are, hold on, need to make a point of checking the live chat once in a while. One time a friend of mine dropped in and said something and I just didn't see it. Anyway. All right, let's go back to reading. Okay. To provide direct label. In our implementation, we use a number of highlight. I don't care. Well, it's not that I don't care, but I'm not interested in that right now. Afterwards, you select course edge to automatically label another row. Yeah, whatever. Once the labeling is completed, we generate a high-resolution stitch mesh by tessellating each face of the input mesh. We begin by determining each edge's tessellation value, Ni, which determines how many stitches will be placed along the edge, importantly the whale edge. We initialize the Ni values based on edge length and the stitch size specified by the user, and then the user can modify the Ni values as desired. We enforce that the 2 whale edges of a polygon are assigned the same tessellation value, hence all whale edges in the same row get the same tessellation value, thereby dividing each row of the labeled input mesh into a number of stitch mesh rows. On the other hand, the tessellation values of the top and bottom edges of a polygon can be different. Yep. In that case, the polygon must contain increases or decreases, figure 12. This is what I just did myself. I guess I could have just read instead of thinking, but you know. Yeah, although apparently this is a pentagon here that they've tessellated, but yeah, that's neat. Oh, fascinating. Interesting. Anyway, let's keep reading. Oops. In that case, increases and decreases are typically placed in the same location of the consecutive rows, resulting in a line pattern forming a seam. Based on this observation, we place the increases and decreases on a polygon near its whale edges so that the user can easily control the position of these seams. That's neat. We also allow, we're back to Death Brain, by the way. Anyway, we also allow the user to mark a whale edge such that all increases and decreases on the polygon are automatically placed along that whale edge only. Huh, that's really cool. I should probably do that too. The tessellation operation begins by tessellating all the edges by inserting vertices that are uniformly spaced along the edge, see figure 12. Then we determine the number of vertices to be placed for each stitch mesh row over each input mesh face by interpolating the total tessellation values on the coarse edges on either side of the face. Finally, we place vertices on the input mesh face using mean value coordinates. Geez, is that barycentric coordinates? Hold on, I gotta look it up. And also, I don't understand how that's relevant. I don't think it matters. You think you could do it in regular coordinates. Oh, I thought this had Fowler for a second. Floater. Oh, it's a generalization of barycentric coordinates. Interesting. There's a lot of math in here. I see a bunch of integrals. Man, do I need to read this too? Oh boy. Well, let's ignore it for now because in principle I don't see why this is relevant. I mean, you could use other coordinates, but maybe there's some reason. And we generate stitch mesh faces using these vertices such that increase-decrease faces, ones with more than 4 vertices, are placed near the marked whale edge. Once the stitch mesh is generated, the user can modify it as we explain in the next section. Yeah, I am not going to do this yet. But yes, it is something, well, it is crucial. It is crucial that knitted garment modeling system allows the user to modify any individual stitch, since a single run stitch can cause highly visible changes in the final model. We have implemented a number of low-level operations that modify the topology and attributes of the stitch mesh. Change stitch type allows specifying the desired stitch model for each face. In our implementation, each stitch type has a particular color, and changing the stitch type changes the color of the face in the interactive window. Set cable edges, and definitely not doing that right now. Finally, split collapse edge can be used on coarse edges, and add remove shift can be used on whale edges to specify increases. Yeah, let's go take a look at that now. Yeah, interesting. So, yeah. Cool. Many knitted garments include repeated knitting patterns. Therefore, we've also developed a number of high-level operations that modify multiple faces of the stitch mesh at once based on a desired pattern. For example, the stitch type of multiple faces on neighboring rows and or columns with a stitch mesh can be changed all at once. This feature can be used to specify common patterns that use alternating K and P stitches, such as rib, garter, and moss. What is this, seed stitch? Anyway, as for more complicated patterns that include increases and decreases, we replace a selected portion of the stitch mesh with a tiled pattern. In our implementation, a pattern is merely a stitch mesh generated on a quad with equal tessellation values on both coarse edges. This controls topology and the stitch type of the faces define the knitting pattern. Some patterns can be tiled entirely and others can be tiled partially, such that a number of stitch mesh faces on either side of each row can be part of a border that is not tiled. To model a pattern, we use low-level editing operations explained above. A pattern can also be created using a text-based description. Each line corresponds to a row of the stitch mesh and lists the stitch types on that row. Figure 14b shows an example pattern model based on the knit instructions in Figure 14a. That's pretty cool. Oh man, I forget all these symbols. So I think this is purl knit. This is yarn over? No, it can't be. This looks like it increased, but I don't understand what it increased. Okay, we can do a little bit of, oh, it says it right here. The real world knitting instructions adapted from blah. And, or the conjunction symbol, is 3-way decrease. Broad arrow is 3-way increase. X is no stitch. Dot is purl, and empty cells are knit. I don't understand. If you do an increase, how can there be the same number of stitches on the next row? That doesn't make sense to me. So here there's a three-way increase. That's a three-way decrease. Oh, duh. If you have an increase and a decrease on the same row, then you're not going to get more stitches. Yeah, this no stitch here, yeah, I get it, I get it. That's neat. That's really neat, actually. Yeah, so this mesh-based relaxation, you know, this is what you get if you just, like, you know what I mean? Like if you have a flat face and you apply just the pentagon shapes, like you'll have a vertex here, 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 and here. And same thing here, but this is not what the stitches would look like if you knit them. So this relaxation is, it's probably something along the lines of, for every vertex, nudge it slightly in the direction that makes all of the faces that are touching it look more like their canonical shape, right? So for example, this three-way decrease or increase or whatever, this three-way decrease would look like a perfect hexagon, ideally. For example, I don't know, let's just say it does though. And then all of these squares would be squares, ideally. Now this shape here is very far from a perfect hexagon, and this shape here is very far from a perfect square. So I'm guessing in relaxation is you just go through the vertices one by one and slowly nudge them to minimize the error for each face that they touch. Something like that. Of course, that's to be done in 3D, which makes things a little bit more complicated. But anyway, there's some, you know, it's basically gradient descent with an interesting error function. And then these are the yarn curves. Yeah. It's very cool, actually. It's very cool. Anyway, where was I? Prepared patterns can be used to replace a number of faces on any stitch mesh with the tile pattern. It either selects a face and automatically finds a group of stitch mesh faces. Yeah, whatever. I'm not doing that right now. I'm just interested. Okay, so this is most likely going to say, hey, we're going to do gradient descent. Yeah, right here. Conjugate gradients algorithm, which is essentially gradient descent with some fancy stuff. Subdivision surface. I don't know what that means. Let me look it up. Oh, subdivision is a place in Toronto, apparently. Descend into the subterranean lair for underground electronic music, located in the heart of downtown Toronto. Oh, it's a club. I've never gone to a club before. But it opens in 15 minutes. It's 9:45, by the way. Yeah. I don't think I'm gonna go. Although they describe themselves as drama-free, whatever that means. Today, somebody named Jimster is playing. Who's that? You can't see, by the way, the screen where I'm Googling this place. Jimster. British deep house producer and DJ. Huh. Yeah, he's coming here to play in Toronto tonight in 15 minutes. Anyway, I'm done goofing around here. All right, come on, let's read this in order. In the previous section, we explained how to generate, or no, how to prepare a stitch mesh That defines the stitch topology of the knitted garment. When the yarn geometry is separated from the stitch mesh, it generally does not have a realistic appearance. Yeah, exactly. This is because the realistic shape of the stitch can be determined in the presence of other stitches around it, and knitted garments often include complicated 3D deformations that are defined by the knitting pattern. Therefore, we use a physically based yarn level relaxation to compute the realistic rest shape of the yarn curves. Since we use yarn level relaxation, the shapes of the stitch models used for generating the yarn level model from the stitch mesh are less important. What? Since we use yarn level relaxation, the shapes of the stitch models used for generating the yarn level model from the stitch mesh are less important. Oh, so they don't do what I was thinking, which is minimize the error between the polygons defined by the stitch mesh and like the ideal shape of the polygons. They don't do that. Hmm. Yeah, varying stitch sizes over the model. Yeah, that'll be another global form of error, is the variation in stitch sizes. Oh yeah, that's right. I was going to look up what subdivision surface. Oh yeah, I got distracted by subdivision being the place in Toronto. What does that mean? Subdivision surface. Oh. Wait, I think I did know what this meant. Hold on. Come on, stop being. In the field of 3D computer graphics, a subdivision surface, sub D, is a curved surface represented by the specification of a coarser polygon mesh and produced by a recursive algorithmic method. The curved surface, the interlaying inner mesh, can be calculated from the coarse mesh. It's the functional limit of an iterative process of each plane. Better approximating this kind of. Oh. Cool. Man, this does not look simple. Maybe it is. Wow, they got an Oscar for it. Yeah, I've seen Catmull Clark before, and I believe they also worked on like a way to do splines or something. We're definitely treading into territory that I don't know much about. But I think I am getting closer to actually knowing how to even start. What I think what I'll do in a second here is, as long as I can. Excuse me. As long as I can. Yeah, if I can subdivide, well, I shouldn't use the term subdivide here. As long as I can tessellate any individual polygon that's either a triangle or a quad and has its whale edges labeled. So long as I can do that, then I can apply it to the whole model. And then I can actually do it all in 2D. Well, that's not quite true. Okay, well, the relaxation. Yeah, they so. Start with a mesh of an arbitrary polyhedron. All the vertices in this mesh shall be called original points. For each face, add a face point. Set each face point to the average of all its original points. Okay. For each edge, add an edge point, which is the average. For each original point, take the average of all n face points for faces touching that point. Take the average of all edge midpoints. Oh, these are the midpoints, not, well, okay, same thing. The average of the two vertices is the same thing as the midpoint. This is the average, not to be confused with, note from the move each original point to the new vertex point. Huh. Actually, it is pretty simple. Oh, in general will not be planar. Oh, fascinating. Uh-huh. But if they're not planar, isn't that a problem? They have to be planar. All right, let's just go check this out and see what they say. I'm starting to lose steam here, but I'll finish at least this section. Mesh-based relaxation first moves the vertices of the stitch mesh onto a subdivision surface defined by the input mesh model. Instead of projecting the stitch mesh vertices directly onto the subdivision surface, we tessellate the input mesh using the subdivision rule and project the vertices onto the surface to compute the barycentric coordinates of the. I'm totally lost here. Which are then used to compute the vertex positions on the subdivided input mesh. What? Is there a picture? Oh boy. Oh man. Well, urine generation I don't care about. Urine level relaxation I really don't care. I'm not even going to do this at all. I'm also not going to do this at all either. Well, I might, but I probably won't. Some nice pictures though. Let's just look at this for a second. Cool. Yeah, I don't care about that. He talks about this in the sorry, they talk about. I have a friend of mine who, without being told the pronouns for another person, even if it appears quote unquote obvious, will always use they them. And that's a habit I'm trying to get into, although it is hard to shake old habits. But anyway, so they here referring to, I suppose, the authors, although I was talking about GEM in their presentation of this paper at SIGGRAPH, when they were talking about the yarn pull-through, they they really struggled with a particular sentence. It was really funny. Anyway, if you watch it, you'll see what I mean. Yeah, I don't care about that for what I'm doing. Results, well, I know what the results are. It looks nice, great. Limitations, generate, yarn frame has certain limitations. The high computational demand of the yarn level, I don't care about that. I do not care. While developing around the topology of the input mesh so that the user can precisely define. On the other hand, this requires users to have some understanding of the knitting process. Well, yeah, I mean, come on. While preparing the input mesh, when they're drawing the object in the first place. Yes, I see. Yes, that is true. Interesting future direction would be decoupling the stitch mesh generation from the input mesh topology in a way that would still allow the user to precisely control the stitch load over the surface. Yeah, actually. Like, for example, at least the way I'm thinking of doing it in my head, I would not be able to deal with polygons that were not triangles or quads. This is kind of a minor issue because you can always split up a polygon into smaller ones. But yeah, I see what they mean, because like, if you, let me draw something here. If you had some crazy shape that was just part of your input mesh that was like this or something, and just the way you defined it, like, actually it doesn't have to be a triangle. Like the real problem is if you have, let me just exaggerate it here. You have something like this where you've set this and that to be your whale edges. Well, now what you've done is you have gone and created yourself a really unfortunate issue where the number of stitches that are dividing this whale edge has to be the same as on this edge. So now you've got like these very differently sized stitches. So the solution here would be to maybe like divide it like this into 2 polygons and then make this a whale edge like that. Should be possible to do that kind of thing automatically, but yeah, to get it to work robustly and to have decent results would take a lot of tweaking and fiddling. A stitch mesh structure provides a very good abstraction for most knit topologies, but obviously it cannot represent everything that can be done with yarn. Yeah, like for example, knit into stitch below is not something that this can represent. At least I don't think easily. Maybe it could, but I doubt it. And the way that they do cables is really kind of a hack, honestly. Yeah. Even though we have not designed the stitch mesh structure to handle knitting patterns that use multiple yarns of different colors in computer graphs, we always modify the yarn color. More importantly, one thing in a real garment is pull loops through anywhere on the garment, not just the loops on the previous row. Oh yeah, you see? This is the knit into stitch below. Such unusual operations for special cases, just adding a pocket on a knitted garment, or knitting pieces of garment separately, disregarding the knitting direction of the seams. Finally, our system requires the stitch layout over the surface to be carefully constructed so that enough stitches are generated everywhere on the surface to allow the final garment to conform realistically to the desired surface. While our offline simulation preserves the shape of the garment, individual stitches may have to deform more than desired as a result of the surface constraints. In other words, the relaxation operations can force the knitted garment to take a shape that is not natural for the number of stitches specified. The top row of figure 23 shows a dress model that does not have enough stitches under the armpit and has too many around the arm. Yeah, exactly. Yeah, that's really funny. Like your armpit hairs would be sticking out of it. In our implementation sharing and at the end of the mesh-based relaxation, we show the user the stretching of each face by color coding. Oh, that's a really good idea. I mean, I thought they just did it for this figure, but actually, duh, it's obvious. It would be really nice to put this in the final thing. Well, I can do that easily because in the way that I'm planning to do relaxation, which is not unlike theirs, but definitely simpler and dumber, is to just for each face calculate an error and then use gradient descent to move the vertices. And since I have to calculate the error anyway, I can just use the error to shade the, shade the polygon. So that's cool. The repeated measurements of the knitted portions be adjusted anywhere. The bottom row of figure 23 shows the final model after the input measures is modified to avoid excessive stretching. An interesting feature would be semi-automatically or totally automatically modifying the stitch layout to better suit the desired garment shape. Yeah, okay. So I think I have extracted most of what I need from looking at this paper. I'll deal with this later, but so number one, I need to take, I have an input polygon, which will be a quad or a tri. Two of the edges will be labeled as whale edges. And we will split it according to our constraints into multiple smaller polygons. I mean, that's pretty much it. Even just that by itself, I should be able to do kind of right now. What's more is that so long as the input polygon is planar, which I expect it to be, I can do this all in 2D, which kind of simplifies things. Now, the authors here go to a lot of trouble, not a lot of trouble, but go to enough trouble to explain that they use mean value coordinates, that there must be some good reason for it, other than, I mean, it's mathematically the same as doing it with raw coordinates, but there must be some advantage, but they just never say what that advantage is. I don't know. Maybe it's just obvious to people who do this kind of thing all the time. Yeah. Well, how long have I been at this? It's also getting, like, late. It's past 10. What's that name? Jimbo or something? Is going to start at subdivision soon. Man, I almost want to go to this club just for the joke. Except I would be a little bit not at ease in a club, if I'm being honest. So, all right, let's take a look at this chick here. Where is that? So let's say that we wanted, let me just take a screenshot so I can draw on it. And go in here. Okay. So, let's say that my whale edges were something like this, right? So, oh my goodness, that's huge. Ugh, oh my God. Okay, hold on. All right, hold on. Let's just go straight to, well, whatever. Okay, hold on. Man, having technical issues here. Just go straight to XCaliDraw, which might work a little better. Here's the drawings from the last thing I was working on, which is the whole thing in and of itself that I'm not going to get into. All right, that's a little better. So let's put the whale edges here, for example. So one here, and so on, right? You get the idea. You see, now we have a problem. Like, well, it's not really a problem per se, but I think it's less than ideal here that this whale edge, even though it belongs to the same row as, say, this whale edge, is much smaller. So, like, here maybe I would want 3 stitch rows, and here maybe I would want 3, 4, 5, 6, 7 stitch rows, and just that does not compute. And one solution would be to redraw like this. Yeah, actually that's not bad. Wait, no, that is bad. Oh yeah, like this. Yeah, there we go. Wait, no. Like this. It's harder than I thought. Yeah, there we go. Now that's a little better. I mean, you could even do this. And now it's a lot more even around the whole thing. So this is something that, the 3D model would just have to have baked into it. I don't know how easily I could do that. Oh. All right, I'm gonna have to take the same approach that the authors do, which is just assume that whatever model we're given makes sense and doesn't have this issue where whale edges in the same band of polygons just don't have huge discrepancies between them. Like if we take a look at the top one here, or this guy here, or actually maybe this picture would be a little better, this one. Right, like that, they're all the same, or they're close to the same. Now this and this are a little off, but it's not too bad, right? Actually, there is an animation somewhere. Let's see if I can find it. No. Yeah. There is an animation. Maybe it's in the SIGGRAPH. Yeah, I think it's in the SIGGRAPH presentation. Let me just go find that. Now that's the yarn level relaxation. Actually, I think I can see what I want in the top picture, come to think of it. Yeah, okay. So, wow, that's pretty cool. So like, what was the edge we had pointed out? Like this edge is pretty short and this edge is pretty long. I mean, not that much longer, but still long enough, right? So that's this and that. And you can tell that these stitches are kind of longer than these ones. But yeah, it all just gets fixed in the mesh-based relaxation. I mean, I would never wear an awkward sweater like this. Like, I don't know, man. I don't know what it is about it, but I would feel so... I don't know how to explain it. The shape of it is just like... I think it's just because the neck is really, really wide. It would show like half of your chest. Like, maybe that's why. Anyway. And there's this hole in the armpit, which we were looking at earlier, which was, yeah. Yeah, so they kind of let the mesh-based relaxation kind of like deal with this issue of the discrepancy in the whale edge lengths. But even so, like these whale edge lengths are still fairly close, right? So we can get away with it in the mesh-based relaxation. Notice though that the price that we paid is that, well, it's a little hard to tell, but I think you can kind of see it better here. It kind of curves up on the side here like that. You see what I mean? And I think like it had to tighten up this edge, which kind of like pulled up here on the side. Not really sure if that's what's really happening, but that's my hunch. Yeah. So, yeah, I think I'm gonna stop soon, but made a lot of progress, at least in terms of understanding. So, we need to write a function that takes in a polygon, a tri or a quad. Let's start with, well, triangles, or let's just write two functions. We'll do one for triangles and one for quads. So we can start with quads, I guess, because that's, to me, the more intuitive one. Excuse me. And we can do it all in 2D. So we'll need a function that takes a 3D quad and just... Oh, fascinating. I wonder if that's the utility of the mean value coordinates, because then you don't really have to... interesting. Oh, man. So we'll need a function that takes in an input polygon and outputs a number of smaller polygons that tessellate the original. And that's like... and then we need to do the mesh-based relaxation, which is a little difficult. I'll have to do some math for that. I'm just thinking. I'm imagining the math for it in my head here. If I include inside the error function that there's a penalty for different size stitches. In other words, if one stitch on one side of the model is a completely different size from the other side of the model, I think it would give me a better final output, because then I won't have stitches of vastly different sizes. But then that means that the error term for one vertex depends on every single other vertex. And yeah, that's fine. Mathematically, there's no problem, but I need to run this on a computer, and I don't want it to be that slow. So it might be enough to just have an error term for disparate stitch sizes in like a small area around one vertex, so that I don't have to go all the way, like run a huge like error function on every single one, that would be good. Yeah, but yeah. 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 I can do this. I can do this. Okay, so now that I know what I need to do, I don't think I'm going to have a GUI for this. I think for now and for a while, what I'll do is I'll just depend on saving intermediate OBJs and opening them in that F3D program. I think that'll be good enough. Although if I want to make this usable, I think in the end I'll have to implement it as like a JavaScript thing to run in a browser. I think that would be the best way. Like, yeah, it is possible to like write a program, say in C++, and compile it and distribute it, except that is a nightmare. Not the least of which because you have to compile it for all the target platforms, and oh hey, we're going to do a GUI in C++. There's literally no nice way to do that. Oh, but you can just use Qt or GTK. Well, listen to yourself, okay? Like, come on. Qt and GTK are just unbelievably complicated beasts that are themselves incredibly difficult to distribute. Oh, but Marco, they get distributed all the time. Yes, but it's still difficult. So yeah, C++ I think is out, even though, or C and C++, you know what I mean, are just out because I just don't want to fight with distributing GUI programs, or even just learning how to make a GUI program in through C++. Like I've tried many times and just gave up because it's just too much of a pain in the ass. I mean, I could maybe use shoot, I forget what it's called. There were actually, I did do this before. SDL, that's what it's called. SDL is actually pretty good. I was able to make a program in SDL that one time, a long time ago, and if you put IMGUI, I believe IMGUI has, well, it almost certainly can target SDL, and so if I was going to do C or C++, I would use IMGUI and SDL, except I don't want to do that. Option number 2 is use Python. I don't know like how much easier it is to distribute a Python program, because on the one hand, if you're using Conda, you should be able to get all that Qt stuff installed, and I'm hoping that PyQt is less painful to use than Qt and C++. I somehow doubt it, mind you. Or there must be some nice Python. I could use that. What is that called? PyTK or tkinter? That's it. Yeah. I could do that, but just between you and me, I really don't like Python that much. Yeah, maybe I will just write it in JavaScript and use a JS canvas. But then loading and saving files in JavaScript is such a pain. Oh man, there's just no good way to do this. It's a pretty good song that's playing right now. I kind of want to see what it is. Oh, we've got Sewer SLVT again. This song is called In Peace. This is one of their calmer songs. It's pretty good though. Yeah, I've only recently discovered Sewer SLVT. But they stopped making music about a year ago, maybe a bit less. And it's kind of a sad story. I think like their significant other died or something, and I think it just threw them into a state of mind where they weren't able to keep producing music and being in, like, being publicly visible in that way. And yeah, it's a shame though, because they're super good. But it's more important that they look after themselves, so it's not that much of a shame. It would be a shame if they kept making music and it made them miserable. Anyway, I'm way off track here, so what was I doing? Oh yeah, I was trying to decide how to do this, like I need to save and load files. I need to draw to a screen. I need to distribute it. These are really, really, really common things. And yet, how come there is no easy way to do any of that? Like, I think Python is probably the easiest for doing all three of those. Except I just hate it. Like, if I'm being honest, I really just don't like Python that much. Wait a second. Hold on. I don't need to distribute it. If I let people run it in Replit, then I don't need to distribute it. Can you upload files easily? So let's take this, open it up in an incognito window so that it doesn't let me edit it. No, hold on. How do you do that here? No. No, you can't upload it. You would have to fork the REPL so that you could edit it and then upload, which is, less than ideal. Man. No, that doesn't work either. All right, let's do a little bit of searching here. Client.js save and load files. There's got to be a way. Oh my God. Oh, it doesn't look so bad actually. Here, let me put it over here. I saw this MS save or open blob, but then I was like, oh, okay, good. That's just for IE10, so I'm just going to ignore that. It's kind of interesting. You create like an invisible link that would download a file, and then click it inside the script, and then it'll download it. That's pretty cool. Now, how do you load a file? JS load file, client.js load file. Man, this is a cool song too. This is Kawaii Razor Blades. Also by Sewer SLVT. I feel silly saying that each time, but I don't want YouTube to ban me. I don't know if you've seen the ProZD videos lately, but anyway. Now, where was I? I keep getting distracted by stuff. if you want to read files on the client using HTML5's file reader, okay. Oh, actually that looks good. Okay, great. I think actually we can do this in client JavaScript, which is also nice because not only does that solve my distribution problem, it also solves drawing to the screen, because drawing to a canvas with JS is pretty nice, actually. It's as nice as it can get in any modern language. And I mean, you could even render to SVG if you wanted. And if you use P3, I believe they have a 3D mode. And P3 is pretty easy to use. That's what Khan Academy uses, which is why I know about it. Or well, Khan Academy uses processing.js, and I'm not sure what the difference is between that and P3, but they're basically the same as far as I can tell. Okay, great. So that's settled it. That's settled it. I will make some JavaScript code to do it. And yeah. Well, I better stop here because I'm getting tired anyway. But before I go, let me at least make a plan for what to do next time I work on this. Set up dev flow for editing JS. There's that, oops, I got the wrong keyboard on. There's that nice Chrome workspace dev tools thing, which I've used before. It is actually pretty good. Need to write up HTML skeleton and code skeleton. Figure out HTML5 file saving loading. Even that by itself could take a lot of time because like web dev stuff to me for whatever reason is hard to do, and then yeah, I'm not going to do a canvas just yet though. I'm just going to have like HTML buttons for loading and saving files or whatever. And then so start by function to tessellate quads needs number of whale stitches as input, needs to generate pentagons for increases, decreases. Oh, that's something I said in my head. I don't think I said it out loud yet. Here, based on the picture, these triangles are like, how do I put this? In other words, based on this picture, it looks like what they're doing is they generate triangles whenever they need an increase or a decrease, and then they merge them with whatever shape is on the other side. And yet in the actual text, they do something a lot simpler, which is what I'm going to do, which is instead of making triangles, just directly make the pentagons. So let me show you the picture where I saw that. Yeah. So they just directly make the pentagons inside the polygon that they're tessellating, which is a lot simpler, and that's what I'm going to do. Increase and decreases. Also needs labeled whale edges. And yeah, that's pretty much it. Nothing much else to say. Oh, I guess I could I might not do this on stream, I might do it just while I'm sitting down looking for something to read, but spend time understanding mean value coordinates. Yeah?